Hello, everyone. My name is Jade, and I'm going to be giving a demo of some Chapel code, kind of working our way up from a fairly simple example to a much more complicated example using distributed code and GPUs and interoperability. All of this code is available. You can access it at this link, and everything that I'm about to show is available there. Um, I'm running this on a cluster, and I have access to some nodes with GPUs, so we'll kind of demo that. But since Chapel is portable, you should be able to run most things on your machine, with the caveat that you might not be able to compile some things if you don't have a Fortran compiler or like an AMD GPU compiler. So let's go ahead and jump into some of this code. Um, Kind of the very first example here is just a very brief intro to programming in Chapel. I'm going to kind of go through some very basic concepts. It's not a complete primer on how to write Chapel code, but it should give you enough background for this demo. So like in many languages, we can write, hello world. Um, Config constants in Chapel are going to be used a lot throughout this demo, and they allow us to have command line options without needing to do extra parsing and handling arguments. The compiler just gives that to us, and that makes it really nice for experimentation. We'll go ahead and declare kind of the main workhorse of Chapel, an array, and we'll initialize it with an arbitrary set of indices. So I'm saying I'm going to initialize my array of integers with indices 1 to n. And just by using a normal for loop, I can initialize this array. So I'll go ahead and run this, and I'm going to use a tool called Mason, which is a package manager for Chapel that will compile and run all of my programs for me. So I can go ahead and compile this program. And so again, this initialization is going to happen in serial. You won't really be able to tell because everything's kind of happening in the background. But once this finishes compiling here, actually, we're going to switch to the non-GPU for right now. So once that finishes compiling, I'll go ahead and run it. And we'll see it run, and you can see it's printing lots of things out, some of which we haven't gotten to in the demo yet. But specifically, I'm printing out this array, which we've initialized in serial. But you'll notice that all these numbers are kind of all over the place and not in order. And that's because we're actually printing it using this for all loop. And the for all loop in Chapel is introducing parallelism. So rather than running this loop in serial, I'm using the for all and saying, I don't care what order these iterations run in, just run it in parallel using my available hardware. And there's a little bit more details to how for all works, but I'm not going to get into that here. You can read the Chapel documentation if you want more details. But suffice to say, it's a parallel loop that gives me parallel computation. So that's why I get everything out of order. So moving on, this is parallel on a single node because I haven't actually asked for distributed code yet. So to do that, I'm going to need to import some modules. I'm going to pull in the block distributed module and some com diagnostics. And so now I can create a distributed array. And in this case, I'm going to use this helper, this blockdist.create array. Exactly as before, I'm creating it with the exact same indices, same type, and then I'm going to initialize it in serial. And if we look at that output in the code here, you'll see that there's no communication when we're running on a single node because my distributed array is only running on one node because I didn't run with multiple nodes. And you can see that here. But if I rerun this with, say, 2 nodes, and now if I come look at that table, go, now there's a bunch of kind of stuff happening. And in this serial initialization, some of the data in my distributed array is on my current node, and some of it's somewhere else. Um, and I really want it to not do this, basically. I want to initialize it where it's available. But a for loop, which is just a serial loop, isn't going to do anything special, right? And so not only is it happening in serial, but there's this extra communication. So the fix is, again, to use for all. So using this for all loop, not only is it parallel on a given node, but this for all loop is, smart about what the type of this domain is, where this distributed data lives. And so the computation inside of this loop is actually going to happen on multiple nodes automatically for me. And so if we come down to the diagnostics for the parallel initialization, now, we have all of this extra work that's happening kind of goes away, and we just end up with this one little execute on. So what's kind of happening on the back end is Chapel code is saying, okay, move computation to this node and then initialize my node. So we get much less communication and it's much more efficient. And once again, we can print it in parallel. This kind of works exactly as before. All I've done is change my array from a single node array to a distributed array, and I can print out my array as before. The last thing I can do is I can be a little explicit with where I want my code to run. So before, these for all loops are running on other nodes, but I'm not saying, which nodes to run on. We can control that in Chapel. So the locales array in Chapel is just an array, and I can access its last element and do stuff with it. So by using an on block, I can move computation to that locale, and then get information about where that code is running. And importantly, for later parts in this demo, I can actually reason about my distributed data and how it's distributed. So for example, I want to know exactly what parts of my array are on my current locale. And if we look down here in the output, I can see that I'm running on locale 1, which is the other locale, not locale 0. And I can see what indices of that array are available. And if I were to run this with more nodes, we'll see that value change. Right. So now I'm only holding a much smaller piece and I'm on locale 7. So moving on to kind of the next example, which before I do, I will pause and see if anyone has any questions.
I have a question.
Yes.
So you started out, your very first loop was the serial loop doing the initialization, and then you used a parallel loop to print it.
Yes.
Would it be accurate to say that like in real code, more commonly you would do the initialization in parallel in order to take advantage of the parallelism, and then to do the printing probably serially or just to print out the array all at once rather than using an explicit loop, so that you sort of had kind of coherence in the data that came out and could maybe interpret it better?
Yes. So if you really cared about like what was printed out, you would want to print this in serial so you can actually, see what is printed. So I could change this to a for loop. But as I think you alluded to, in Chapel, I don't even need to write a loop to print my array. I can just print the array, and Chapel will take care of printing that for me nicely. So yes.
Great, thanks.
All right. Moving on to the next code, which is we're going to do a little bit more interesting work. One of which is we're going to declare a function. And let me go over to that code. So this is declaring a function. And you'll notice that I've declared this function without any types. This does not imply that there's kind of dynamic stuff happening. What's actually happening is these types are being inferred by the compiler at compile time. So this is a compiled procedure, but it is completely generic about the array and domain. And what we'll do is we'll declare, using these same generics, we'll declare an output array, which has the exact same type as the input array. So if, for example, the input array is a distributed array, the output array is also a distributed array, distributed in the same way. And then we'll go ahead and initialize it in parallel doing an iteration over that domain. And this is a pretty simple stencil. We're only working in one dimension. And what we're doing is just doing a mean of the element and its two siblings. So accessing the element to the right or in front of it and behind it, summing them all together and dividing by 3. And this is, again, happening in parallel because we want to do our work in parallel. So this function is going to get used a couple times throughout this. You'll see here I have a couple of config constants for this program. And then we declare these domains. And I've done something a little sneaky here. So I've declared that I want my data to be over this 1 to n domain. But I'm actually declaring the halo domain to be 1 bigger than that. And so the reason I want this halo domain is that way in this code, you can see I don't have any boundary checks. By iterating, I can declare the data over the halo domain, but the only data I will ever actually care about is the data domain. And so that allows me to allocate a little bit extra data, but maybe avoid the overhead of checking the boundaries. So like I said, we'll initialize the array with the slightly bigger domain, the halo domain, and I'm just going to fill it with some random integers. This is just a library routine using Chapel's random module. And notice that because this domain here is not declared as any kind of parallel or distributed domain, it's all on this one node. This array is also on one node. And here, I'll just print out the arrays. You'll see here, I'm printing out the arrays just normally. I don't need to write a loop to do it. And then I can go ahead and call that stencil. And so now here, I'm passing in the domain I want to iterate over, so the domain I actually care about, and then the array. And then I'll get back my array. And then when I print it out, I'm going to print out the array, but only the part that I actually care about. So I can take the data domain and I can slice my array that has more data than I care about to actually see what's interesting. And so if I build this and run it, we'll see that in just a moment. Yes, that is everything for this file. So we should just see that output. So if I go ahead and run this, so you can see here Chapel's taking care of printing my arrays nicely in order for me. The numbers that we're seeing here don't matter too much. They're just random numbers, so don't try and get too much meaning from them. But what you should be able to see is that, yes, I can print my array, and yes, I can print a slice of that array, the part that I actually care about. And all of this is being computed using my function. So this is a pretty simple stencil that just a single locale. And the next example, we'll kind of take this to the next level with distributed code. Before I do that, does anyone have any questions? All right. So going into the distributed code, if you notice, this stencil and this stencil are identical. So I haven't changed the actual definition of my computation. All I'm changing, and hold on. We'll just have to live with that. All right. So this is about the same. I haven't really changed anything. And I'm going to now distribute my data rather than using, like before, I had kind of this basic domain on a single node. Now I'm going to declare it using this block dist. And so now I'm saying my data is distributed over as many nodes as are available to me. Like before, the array initialization and filling the random are exactly the same as before. And pretty much the rest of this code is the same. The one difference is I'm adding this com diagnostics to see what's going on. So let me go ahead and go run this. And if I run it with just one locale, we won't see much difference. We won't see much difference because I haven't asked for more locales. So this is basically the same as the normal single locale array. But if I run it with, say, 4 locales, we'll see it, doing something more interesting and doing lots of communication. I can find the output. Here we go. Here we go. So I've got lots of communication that's happening, and I can print out my array. Again, this is the exact same function. It's just because I've changed the array, I'm getting distributed computation now. And I'm actually going to run this. So to kind of show off those config const, I'm going to run this with a slightly smaller amount of data just so it's easier to fit on the screen. There we go. So you can now really clearly see the data on a single line here, although we're not using very much data. So all I've done to make this distributed code is basically change the definition of this domain, which is pretty cool. I didn't really need to change anything else. But one thing that I'm going to do slightly differently now is rather than using this default block distributed, which is just going to partition indices across my nodes, I'm going to use something that's more tailored for this application, which is called a stencil dist. And when you're using the block distributed domain, you're going to get excess communication because elements that are, when you're doing this stencil computation, elements that are next to each other but are on different nodes are going to need to communicate. And we don't want that. So we're going to use stencil dist, which handles that by saying, how much data to duplicate on each of those nodes so that the core computation doesn't need to do that extra communication. And I'll point out, again, all I'm going to do here is I'm going to change the definition of the data domain, and everything else stays the exact same, and I can run my code. So if I now scroll down, everything stays the exact same, and I get my next array. One thing that I will point out is there's ever so slightly more communication that is happening with the stencil distribution, because what's happening here is you can see there's communication that's happening on locale 0. This is trying to get boundary elements. But if I move to the stencil distribution, that communication disappears because those boundary elements are duplicated. So I don't need to do communication for them. And that communication is kind of moved elsewhere. And we really won't see an effect like on a performance improvement where this communication gets moved until we run this in a loop, which we won't really do in this demo. And we'll talk about what you need to do when it's run in a loop. But kind of for the purposes of this demo, we only ever run it like 1 or 2 times. But I do want to point out, the importance of this distribution. So I will pause here and see if anyone has any questions about this distributed example, kind of taking the simple stencil and turning it into distributed stencil just by changing the domain.
I had a question. It's more, I think, back on when you went from the single locale to the distributed here. I think between the original hello example you showed and this one, you've used 2 different idioms to describe distributed domains. One was like a create domain factory function. The other was this dmapped statement or expression. Are those essentially equivalent to one another?
Those are essentially equivalent to one another. For common cases that create array or create domain factory function handles a lot of simple cases cleaner. But the dmapped function kind of gives you the full control over the application. But they do the same thing.
Okay, thank you.
All right. So now we've been doing this computation in Chapel, but not everyone wants to write Chapel code. What if I want to write something different? And so I'm going to move over to this interop code. And so now I'm instead of doing the work in Chapel Land, I'm going to do it in C. And so I'll declare here I've got some function somewhere else that's in C, and I'm going to call it. And if you're curious what that looks like, it's just a simple for loop in C. But this could be, your OpenMP code, your whatever you want it to be. Um, and then we're going to call it from Chapel. And so this should look somewhat similar, at least the beginning, right? I declare my stencil function, I declare my output array. But now I'm going to kind of get into some lower level details of the stencil. So now I'm going to explicitly do my parallelization or my multi-node communication because I'm doing the actual computation in C. So what I'm going to do here is I'm going to say for each of the locales of my domain, I want to move computation to it. So what this idiom is saying is in parallel, give me a task on each of my distributed nodes that has a piece of the data. On that node, oh, okay. Zoom's getting in the way here. Um, I'm going to grab that local piece of the data, and this is going to include the duplicated elements. And then I'm just going to call the C function. There's not really too much interesting here. It's just this is the interesting part is I'm moving computation to the nodes, and then within that node, I'll call out to some function. I'm going to assume that this function will handle parallelization, optimization, whatever for me. And you may not be surprised to learn that from this point on, the code stays pretty much the same. So here I'm just skipping right to using stencil dist. This is the exact same domain as before, same array, same printing, all the way down to calling the function. And so everything in the rest of my code pretty much stays the same. All I have done is kind of replace this for all loop with this more explicit co for all on, and then calling out to C. And so everything will now work the same. If I build that and run that, and we'll run it on 8 locales, why not? And we'll just reduce the amount of data here. Okay, so again, you can see the communication that's happening when we call it in C. All of this communication is handled by Chapel. All of the computation is done in C. So that's pretty great, but what if I don't want to write in C? What if I want to write in something else? Like, say, Fortran. If you'll notice here, this code is pretty much the exact same as the code above. Whereas before, I had my stencil in C, now I have my stencil in Fortran. And the function is pretty much the same, and the code for all is pretty much the same. But now I'm calling Fortran code. And if you really care, the Fortran code is here. I'm not a Fortran expert, but you could write, whatever Fortran code you want here. And then pretty much the code stays the exact same from here. All I've done is swap out my stencil in C with my stencil in Fortran. Now, one thing I'm going to do slightly differently is I'm going to reuse the previous array and do kind of another manual iteration. And this is what I was talking about earlier with stencil. Because those elements are duplicated, we need to update the halo. And so that just gets done by calling update fluff. So if you were to do this in a loop, you would say, for I in my domain, you would do your computation, and then you would update your fluff. But we're only doing kind of manual iterations. So we don't need to worry about that too much. But we'll see here when we update the fluff, there's a bunch of communication that happens because we've updated the fluff. And the reason we do this is we don't want the updating the fluff to interrupt the core computation. So then after that kind of fluff update, everything is going to look pretty much the same. We're going to call out to Fortran and print out our arrays, slicing our arrays like before. And so you get kind of that output from Fortran. Um, so you can kind of drive your computation from whatever language you want, but driving it from Chapel using Chapel's communication, you can use C, Fortran, pick your favorite language as long as it has a way to talk to C, it has a way to talk to Chapel. Any questions about this kind of interop example and distributed code before I move to GPUs?
Not here.
All right. Moving right along to GPUs. So I'm going to switch my directories again, and I'm going to switch the Chapel compiler. The Chapel compiler has a GPU mode and a non-GPU mode. So now I'm in GPU mode. This is just kind of setting some environment variables for me. And we'll go ahead and build this. Okay. So one thing that's kind of really cool to note here is, for the most part, this function looks the exact same as all the other stencils that I've written. The one kind of difference between the GPU stencil and this distributed stencil is, rather than declaring the array in the function and returning it, in the GPU stencil, I'm just passing in a reference to the array and then modifying that reference. But the core loop is pretty much the exact same. And we will now kind of combine this bit with the bit from the interrupt bit, where we can move our computation to our various nodes, and then move computation to our GPUs. And in Chapel, you have locales, like these top-level target locales, moving computation to my node, and you have sublocales, which is, for example, a GPU. And so here I'm just saying, this is grabbing the local domain of my indices on my node. And then I can go to my GPU and allocate GPU memory. And so here I'm copying the local indices of the CPU array to the GPU. I'm allocating memory for my GPU kernel. I'm calling my GPU kernel, and then I'm copying the result back. And this is it to do GPU computation in Chapel. Right, I have basically the same loop. I need to do a little bit more work to kind of drive where this computation occurs, but more or less the same. And the way that I call it is pretty much exactly the same. This might be kind of familiar by now. We allocate our stencil dist, create domain, distributed domain, create our Halo domain, create our array, print it, and then call it. Great. Let's run it. And I'm going to just right off the bat start with one locale and use kind of a much smaller data size just so it fits on the screen. Perfect. So as I scroll up here, we can see our original array. We're running on one locale, so there's no communication that's happening. But I'm also printing out these GPU diagnostics, and we can see here are these kernel launches that are happening. And then we've printed out the array. If I bump this up to two locales, we'll see more communication, and give it a moment. There it goes. So I've got a little bit more communication because I'm communicating across nodes. Fortunately, this is kind of wrapping badly, but that's okay. And now I'm seeing, here's the launches from my first node, and here's my launches from my second node. So great. However, this machine, I think, has 4 GPUs per node. And right now, we are only using the first GPU. So, wouldn't we like to use all of those GPUs? And that's pretty easy to do. I don't need to change my kernel. I'm just going to kind of change that driving function. And this kind of beginning part doesn't change much. What is going to change, and actually the calling is not going to change much. What is going to change is I'm going to call multiple GPUs rather than just a single GPU. So here what I'm doing is I'm going to create a task per GPU. So that's iterating over these GPUs. And I'm going to use this library function range chunk to chunk up my domain for the number of GPUs. So what this is doing is giving each GPU something to do. Um, and we iterate over that. I have the kind of the chunk, the slice that I should be using. And I have the GPU that I should be using. And then everything kind of happens like before. The one slightly different thing I'm going to do here is rather than directly slicing the array off of this range, I'm going to slice it off of a domain. So I use that local chunk to create a local domain, which is that GPU domain. And then I just do the computation like before. And the rest of this code stays pretty much the same. If we look at the output here, I don't think I gave it enough data. Let's give it more data. There we go. So if we come up here, now we can see, for multiple GPUs, still got the same COM diagnostics as before, but now there's way more kernel launches than before, right? Before we were seeing, let's see, 2 kernel launches, 2 copies, and now we're seeing 8. And we're seeing 8 because we have 4 GPUs, 4 times 2 is 8. And that's happening on both of these nodes. And I'm going to need to bump up the data size here. And while I do that, I'm going to turn off printing arrays just so the screen stays a little cleaner and bump up the number of nodes here. Now, the reason I need more data is kind of the GPUs need data, otherwise it's not really worth it. And some memory errors might occur if you try and pass like 10 elements to 16 GPUs. That's not going to work too well. And we'll give this a moment. I hope it works. Well, while that's working, that let's see if we can get this to run. There we go. So now I'm using, I think, 4 nodes. So I'm getting all the GPUs on all of those nodes. So that's great. What if I don't want to write my GPU kernels in GPUs or in Chapel? Right? Like, I think this is a pretty clean way to write a GPU kernel. But you could have existing kernels. You could have, you could really like writing CUDA or HIP. So I've written a kind of little header here, and I'm going to pull up the actual HIP code. This is my silly little GPU kernel written in HIP. I'm not a HIP expert. Please don't judge my HIP code. And I'll have this little C function that will handle doing the kernel launch through the HIP API. It's also going to handle the copies from CPU memory to GPU memory. You could do these copies in Chapel land. I chose to do them in HIP land just to do something a little different. And everything is going to kind of work exactly like before. This is pretty much the exact same loop that we had above for our multi-GPU example. But instead of calling that GPU kernel that I wrote, and instead of copying the data, because again, this HIP function is copying the data, I'm just going to call out to this extern C function, which is going to call this GPU function, and everything will just work. And again, the rest of the code stays the same. And we come down here, we see, stuff's happening. The one thing I will note is now you no longer see these diagnostics for the GPU because these are counting like Chapel kernel launches, not like other kernel launches that aren't in Chapel's control. But I can't promise you that it's doing something. If I turn back on printing the arrays, you would see it doing something. Um, and turn this off just to prove it, but um, I'll let you trust me with that. Um, if we don't get GPU crashes, there we go. So there's all that data. It's doing interesting things. Um, any questions about that?
So what do you attribute that GPU crash you just encountered?
Um, I have noticed a little bit of instability on this system. Sometimes this code runs perfectly, other times it crashes. Um, I would not be surprised if there is a bug in this kernel that I wrote. There's kind of a lot of low-level memory copies that I'm doing here. I would not be surprised if there's a bug in that I haven't found, which is crashing. Um, it only seems to happen with this external GPU. It doesn't happen if I take out that interrupt. So I'm pretty sure it's a bug in here somewhere.
Okay, cool.
And
Makes
also
sense.
there's, as you can maybe see in this demo, I am using a cluster and shared resource, so I do have to, share nodes with other people.
Okay, thank you.
Any other questions? And I will say that this is the end of my prepared content for this demo. So I can take any questions about anything that I've talked about today.
I think I'm good personally. Thank you.
In that case, thank you all very much. And as a quick reminder at the end of this, all of this code is available. You can go look at it, critique it, review it, whatever you would like, right here. And yeah, thank you all very much.
Great. Thanks, Jade.